in attendance? Do you want to report so I can resume?
Hello, everyone. Welcome to our lecture. Today, we'll be talking about transformers, so basically continuing all the lectures we had previously. Before we begin, please fill in the attendance poll on Piazza, and then we will continue with the lecture.
And today we have a lot of content, so please bear with us. We'll probably go a little faster than usual. And if you have any questions, feel free to ask on the relevant Piazza post for today's lecture, and the TAs will be able to help you.
All right, great. Hopefully, everyone will fill in the Piazza attendance post. Briefly outline what we'll be talking today. So first of all, we'll cover transformer architecture, following up on the previous lecture that Professor delivered last week. Then we will briefly talk about how to train and fine-tune transformers. Then we will also talk about transformer applications, so how we can use it, with what kind of data, should we make any modifications. And finally, we will have a separate case study on LLMs as one of the case of data modalities that could be used. All right, to begin with, you guys all saw this framework, and it's been presented in multiple papers and currently used very highly. At this lecture, we were trying to get step by step how this thing was built and how we can use in our projects, work, and everything. You might see lots of words associated with this paper or with this architecture. It might be a lot, but we will be trying today to cover that by step, and hopefully will give you a better guidance and understanding how it all works. All right, to begin with, let's start with the task. So our task for this particular case is a translation. So we have an input in English language, I ate an apple, and we really want to translate it into German. Ich habe einen Apfel gegessen. This task is really interesting because we need to come up with some interesting model that will help us to encode our inputs in a very smart way and be able to convert the input stream from one language to another. There are multiple ways of doing this, and in the previous lectures, we were covering various RNN techniques, how we can actually make this transformation. But today, we will be talking about how we can use transformer to perform this language translation. The first and very first step, we need to do something with our inputs to make them more appropriate for our model. If we just, of course, we can just input whatever we have right now as a string, but the results won't be as we want. So the first step we really want to do something. Sometimes we can use, in this example, we're using tokenizer. So the simplest step we can use with this string, I ate an apple, is just to split it into individual words. Tokenizers could be different. We can split them by character, we can split them by word, we can split them by multiple words, but the main goal is to make it a little bit more separate. So this is step number one. Once we have this, we really want to do a second step using an embedding layer. So trying to create an embedding of these words. So the similar words would be more closer to each other. For example, if we have apple and pear, it will be closer compared to apple and the house or something. For this, we may use multiple embedding strategies. And in the end, we will receive some sort of embedding of our words that will be basically incorporating the relationship between those words. Once we have these layers, and once we have these transformations, we can move on to the next part. So what we did here, basically, so we took our raw string, we separated it by words, we added, we transformed it into the embedding, and now we move on to the second part. As you remember from RNN LSTMs, previously, they already incorporated the position of the word. So it was very clear, are we on the start of the sentence or on the end of the sentence? When we use this type of architectures, we don't have these properties. So we need to come up with some smart way, as you talked previously in the previous lecture, how we can encode the position of the word in the sentence. Because currently, if we have two separate strings, we have I ate an apple and end of sentence character, and apple ate and I. As of current situation that we have with our model, the model won't be able to tell the difference between those. So we need to do something with our word embeddings to make sure that we also incorporate the relative position of the word in a sentence. And there are multiple ways of doing this. And so what authors of the original paper were thinking, there are multiple ways of doing this. Before we move on to this, I remember we also discussed this topic with the professor last lecture. So question to the audience, maybe we can generate the person who can answer, what would be the requirements of this positional encoding? What is very important? What should we do with our original embedding to make sure that it also incorporates the position? Do we have? Could you?
Gray falcon.
Gray falcon? Who is that? Is Gray falcon in the room, Zoom, or in person?
Ketan Chaudhary.
Yeah, I'm here.
Yeah. Yeah.
Sorry, can you repeat the question?
Yes, a quick question. What would be the requirements for positional encoding? What do we need? What would be the properties of this positional encoding to make sure it incorporates and accounts for the relative position of the word? Basically, what was discussed in previous lecture.
I'm sorry, I don't know.
So imagine if we have particular sentence and we have a word, we need to do something with this. And for example, we have 5 words, and each word has a number 1, 2, 3, 4, 5. We need to do something with 1, 2, 3, 4, 5, add, multiply, do any transformation to make sure that the new output, it already also accounts for the position of the word. Yeah.
I think we did a weighted cosine similarity.
One of the ways to do that as well. Yes, this is one of the ways we can use sine, cosine. It was previously discussed in the previous lectures. We can also account for the positional position in the word. So important to account, we have some representation of time, and also it should be unique. So if we add exactly the same thing to all of the words, it won't matter. And so there are multiple ways of doing this. We can add something, multiply, but if we're doing, as possible candidate just adding something, the key issue we have is it's unbounded. So the third criteria should be also bounded. So the main criteria and the main requirements of position encodings, it should have some representation of time, it should be unique, and also it should be bounded. This is the main requirements. And so what was proposed in the original paper is that what if we have some matrix M that will be multiplied by the original embedding, and it will help us to produce these unique positional encodings. This matrix M should have a few properties. It should be unitary matrix. It should preserve the norm. This matrix M could be learned in the process. And as a result, it will produce unique embeddings at each time. And so this is the original paper where this concept was introduced. And basically, we're using sine and cosine in positional encoding. And so the final formula that was introduced here, you can see there are those two set of formulas. We have different indices, and we have separate formula for odd versus even embedding indices. And so we calculate for each embedding, we calculate additional positional encoding that is unique and help us to differentiate between different positions of different words. Once we calculate it, so we take the original input, we calculated the embedding, now we have the position, we add them all together, and now our embedding is not only includes the original embedding, but also the position. And it's very useful for our model later to use it in next stages. So as of now, we could see we started with an input, I ate an apple, we use a tokenizer, we split the words, we use the embedding, and then we also added the positional encoding. So now our embedding, the resulting sequence, the resulting is very contextually rich and incorporates positional encoding. Okay, so as of now, we discussed tokenization. We discussed, yeah.
So now you're using two different functions for the odd and even. I mean, why using a different sign for maybe the even and
Yeah.
why use the two?
The original paper experimented with multiple techniques, and they found if we use them separate, it helps to incorporate the differences between those. It helps to incorporate better the position of the words. If we use them separate, comparatively use like exactly the same for both even and odd. Yeah.
For one more question.
Yeah.
Maybe I missed it, but why do you use 10,000 as a base?
Oh, it's copied from the original paper. So its original formula was introduced in this paper. Yeah, here.
Okay.
Yeah. In the interest of time, it would be great if we just leave all the questions till the end. Yeah. I'll post in the Piata thread. So as of now, we discussed tokenization, we discussed input embeddings, we discussed position encodings, and now we're ready to move on to the main goal of the entire transformers is basically the attention mechanism. So as of now, we're thinking about the transformer as transforming one input sequence to another, to the output sequence, and the main concept that helps us to make it conversion really effective is the attention mechanism. So the attention mechanism, imagine, so we have this output embeddings. We're trying to think like to which embedding we should pay in the closest attention, because it will help us to know like which will play the biggest role into translation. So like if we have translation, like to translate the word I, to which part of the input we should be paying closest attention to get this correct translation. And how we do this, so we need to come up with a way how we can calculate those weights. And those weights, as you remember from previous lectures, these alpha weights. So we need to calculate with some matrix alpha that we'll be able to multiply our original embeddings by some sort of weights, and they will help us to understand how important is particular input for a particular output that we are predicting. You remember this formula? It was discussed previously, and it has three important components, query, key, and value. And now if we want to recap briefly how it's all been done, so we can remember to a database example. Imagine you have this table, and you have key and values. So you have different order numbers, and each order number is associated with specific information. What query is doing, they just basically build in a question that we are looking for example, the order details of order 104, and then this query helps us to find associated key and then a value. And all of this, if we have multiple questions, they could be done, all of them at the same time. So to summarize, we have a query that basically search for information, has a relative question. Then we have key that basically answers this question, and then value that provides an information. And if we see, all this information could be done in parallel. So we have query, key value, and then key and separate value. If we go briefly through the slides that were presented previously, so imagine we have four different words plus like end of sequence character. For each of these words, we calculate, initialize query, keys, and values, the separate matrices. Then in step one, as you remember, we multiply keys by queries. We get the vector. Then we calculate, pass it through a softmax, and get an attention weight. And after that, we do this for every single token, and they get a contextually rich embedding. So this is all the steps that we do to get the attention, to introduce attention in our calculations. And the unique part about this, it could be done in parallel, so we don't need to wait when we will build attention for token number 1 before we start the token number 2. It could be all done in parallel. All right, so at this point, we discussed how we take the original inputs, how we tokenize them, how we build the embedding, how we add the position to the token, and also how to account to which part of this input should we pay the closest attention using the attention mechanism. And now we move on to the different parts. Yeah, and we have a poll. We can keep it here.
All right, probably just 30 seconds for the poll. Please let me know if that's being posed. All right, so everyone ready? Everyone done the poll? All right. You should already know this, right? You already answers. For a particular attention weight, you use the query for that, and for it to query all the other actual tokens, right? Because the way to think about it is that to update the representation for L2, you want L2 to ask all the other tokens, what do you mean to me, right? So the query comes from Q2, and the key value comes from other tokens. And the last one, that's very obvious. Right? If you have a question, please post on Piazza so we can help you asynchronously. All right, so let's talk about the next component of the encoder block, which is called self-attention. And self-attention is not that different from attention. It's actually exactly the same as attention, which means it's exactly the same as this particular formula right here. And the particular motivation for the self-attention module is because if you have a sentence like this, right, and obviously the word it here means something else in the same sentence, right? There's no way that it could mean something on its own, right? But what exactly does it mean? If it means animal, then the representation for, or the token embedding for the token it must be similar or even the same as the other word that it means, right? Or else, if the it means street, that'll happen as well. So what do we actually do when we have a reference solution like this? What if, if we want to encode this rule of having the word it take the representation of another token, then what token does it actually take, right? What exactly does it mean here? And there's no way to encode this in a rule-based way.
Not
right?
enough audible.
Excuse me, is there a question on Zoom?
Could you adjust your mic? You're not that clear. Your audio is not that clear on Zoom.
All right, sorry. Here. It's probably, is it better?
Yeah, that's better.
Oh, yeah, cool. All right, is it better now?
That's much.
All right, cool. So as I said, self-attention, mainly the motivation for that is just to solve the co-reference solution where we have a word that clearly references another word or token, but then there is no way for us to infer rule-based what that word actually means. So here, every token can refer to any other token in a sentence, right? It can happen for any token as well. So we have to have a general or generic solution to update any word's token representation to incorporate other representations from distinct tokens in the sentence, right? And so here's where self-attention comes in. So basically what happens, we probably want to clip it here. All right, so basically what happens is that we still have that same formula with QKV, but then the input for all these modules, so the input for Q, for K, and for V are exactly the same. And that is the representation or the hidden state for this module to start with. But that actually doesn't mean that the QKV matrices are the same. It just means that the starting point or the input to the transformation of QKV are the same. And so here's what I mean by this. So if we think about how the QKV are generated, it actually means multiplying the input embeddings of the token itself to the WQ, WK, and WV, right? So in here, by the same input, we actually just mean that the input embeddings is the same, but then it's got to get multiplied with the WQ, WK, and WV, so then you actually have different QKV matrices. Like the matrices are not the same, but the input for those are the same, right? It's clear?
All right. So then, as I said, you have the input embeddings and you multiply to the different transformation matrices, and now you have the projections for different components of attention, and the relevant dimensions are written up here. Hopefully it's clear. So yeah. And when you throw the QKV into the attention formula, you have something like this, right? You have the Q projection and you multiply it with the the transpose of the K projection, and you normalize that by the dimensionality of the hidden state, right? And the runtime complexity of that is T squared times D model if you're doing it the most inefficient way, which basically just means a bunch of nested for loops. But in reality, as with your experience with homework part ones might tell you, there are often ways to optimize beyond this obvious baseline. So then the complexity here actually is just a big O notation, and so instead of the actual runtime of the implementation of these packages like in PyTorch, it's going to be more efficient than this. And then in the end, you take a softmax based on the attention weights, and then you use that as sort of the weight to take a weighted average for all the different values in here. All right, so once you have that in place, then that will basically give you an attention representation of any different of any particular token, and let's call it Z, right? And the dimensionality of that is exactly the same as before that token passed attention. But the only difference is that now that token has taken in the representation of the other tokens as opposed to just being the embedding of that token itself, right? And the dimensionality is the same. So the short takeaway is that attention does not change the dimensionality of tokens. All right, so now we have the coreference solution, and it turns out that attention can actually solve a lot of other problems, namely these, right? And then all of these different problems that attention can solve, we don't actually encode specific rules for attention to solve. We actually just give the neural model pathways to pick up possible ways to solve the problem, and it's actually up to the model and backprop itself for the model to know how actually to solve this problem by learning efficient attention weights. But then the idea is that we just make it possible for the model, so the model will have a pathway to learn it by itself. All right, so here, what you actually will notice is that this diagram actually says multi-head attention instead of just attention, right? And what that means is actually, if we go back to the projection matrices here, where we multiply each of the input embeddings to 3 different projections, then it's actually possible for us to split the projections into smaller sizes. So basically, you notice how now the dimension for the projection sizes is going to be written as d model times d model. So then it turns out that if we want to have h heads, then that's actually just going to be exactly the same as when we have just one head in the total number of parameters. But then each of those heads is going to have a smaller projection that projects the input embeddings to a smaller dimensionality. And the reason for that is because we want a consistency to enable the same attention module to be plugged into the same model despite changing the number of heads. But then the motivation is that different attention heads might learn to pick up different semantic properties or learn to solve a different set of these issues that might arise in the learning of natural language material. So if we have h heads, then the dimensionality of each head is just going to be a fraction divided by h of the original dimensionality. And you do the same thing, right? You multiply the inputs to each of these heads, and then you get projected matrices for Q, K, and V. And you do that, you throw that into the same attention formula for each head. And then in the end, you concatenate the representation for each head together. So then you have different pathways for the model to essentially distill the same material, but then that's going to be easier for the model to, if it actually wants to solve different semantic problems in each attention head, because that's a different set of parameters. Right, does this make sense? All right, cool. So here we have successfully showed how attention might be able to update the representation for each token to solve these particular problems. And then after multi-head attention, what you might notice is that in the diagram, you have what's called feed forward. And that is actually not anything different from just the basic MLP, which you built in, I think, the first homework. So then it's just going to be an MLP with a nonlinearity activation at the end. And the reason we want that is because we want nonlinearity in relationships. Because if you remember from before, apart from the softmax, everything in the tension is just matrix multiplication. And then we want to have a different layer of complexity. So then the model can actually learn nonlinear functions with complex behaviors. All right. And after feed forward, we actually have what's called add a norm. And what that is also very simple. The norm actually just means normalizing the attention representation to a given mean and standard deviation. And the reason for that is because we want to stabilize the training and we want to have regularization in order for the model to avoid overfitting on a specific subset of materials. And also we have residual connection, which is what people usually do these days in large models, just because as models grow larger, you want to have gradients that are still trainable, right? If you don't have these residual connections, then the chances are the gradients is going to either vanish or explode near the end. So then this is for training purposes, so that we can train deeper networks this way. So this is what's meant by the feed forward and add a norm that goes after the attention. All right, and so here's the complete picture, and then that is called one encoder block. Right? And what happens in the model is that you actually have a number of these encoder blocks. And each of these blocks are not going to change the dimensionality of the token embedding in any way. So then you can stack them on top of each other as much as you'd like. Right? So the input to each encoder is just going to be the output directly from the preceding encoder block. All right. So sorry, so far we have talked about all these issues, and let's talk about go back to our original machine translation example. So here, we want to translate English into German, right, or any other language. And so what happens is that we have the targets, and we want to make sure that the model has a big probability of decoding into the correct token when the decoder decodes its internal representations, right? And so what happens is that the target is also going to be divided up into tokens. And so then the target goes to the tokenizer, and then, as I said, it goes to all these little blue tokens over here. And then it goes to the embedding layer and positional encoding. This is exactly the same as in the encoder. And so in the end, we have a token embedding for each token, each shifted by a little bit in a sinusoidal way. As Kate explained, so then the model actually knows which tokens come before or after each other. Right. So then during training, we actually have the full ground truth, meaning that if we want the input English sentence, I ate an apple, to translate to this German sentence, then this whole German sentence is actually available as a training material. So that's the reason why we have this whole material available for training to be able to go to the tokenizer and to go to the positional encoding, because this is a training material, right? And if the model is actually outputting the translated sentence, then it's just going to have part of that, and we're going to delve into that later. So during training, we want to make sure that the model will generate each token given all preceding tokens, even in the encoded, even in the decoded answer, right? So the model will generate each given SOS and HAVA given each NSOS and so forth, right? So if we look into the attention part, so how are we going to have the model update the token representation of each token given all the other tokens, right? And the usual decoding strategy is that, as I said, you want to have the model predict each token only given the preceding tokens, right? Because during actual inference of the model, there's no way that the model can know what a token is before knowing what its preceding token is, because that's how the decoder decodes material, right? It takes in tokens sequentially. It does not take in tokens any other way. So the big question is then, how can we parallelize the training regime for such a decoding strategy? Because if you think about it, during training of the decoder, each token should only pay attention to the outputs that come before it. Because, as I said, the decoder will not know what token came after it if it's only generating the token that we're caring about, right? So if we're generating a token t, then there's no way we can know token t plus 1 beforehand, right? Because the sentence goes sequentially, and that's the way a decoder takes material in. So if that's the case, then the attention weights should also be 0, or the model should also not pay any attention during training, even when we do have this training material. The model should not learn to pay attention to later decoded outputs when it's training to decode, because if the model actually trains that way, then the model is going to actually assign attention weights to token places or token pairs that are actually not going to be existent during actual inference. So those part of the weights are going to be useless in actual inference. Right? So we actually want the decoder to learn only to assign attention weights to token pairs that can realistically appear during actual inference. Right? So here, these gray tokens should not be paid attention to. Because, let's take the first line, right? During SOS, the model is try to generate each. So without each, it's not going to see any other token. So the model should not have any attention weights for that either. So the reason, so the way how we do that is we literally set the token embedding to negative infinity for all these tokens. And the reason is because when we later throw into softmax, then that's essentially just going to be 0 for us. So the model will not have any attention. So I think I missed the book. So it's not the token embeddings that we set to negative infinity, but the attention weights. And then in reality, I mean, I hear say it's going to be negative infinity, but in reality, it's usually enough to just set it to a large negative number. So let's say negative a couple hundred. It's usually just enough. All right. So this is what's called a masked multi-head attention. So basically, first of all, as I said, multi-head attention is just attention, right? So the attention mask essentially makes it safe that the model is just going to pay attention to existing tokens. So that makes the training and the inference the same task, right? Because otherwise it's going to be a mismatch. And this is also, by the way, this is also what's called a causal attention mask. You might have heard the word causal LM. If you go to Hugging Face, then all the models it's going to be named as blah 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 for causal LM. So this is what causal LM is. The word causal means that the later tokens are caused by earlier tokens. So that's what the word causal means. And LM just means language modeling. So then once you filter the attention mask by a dark triangle this way, then that's called causal language modeling. All right, and you use the mask attention weights to combine with the values to give you the updated representations for each token. And then you do the same story. You add a norm, and then that basically is the same as the encoder block. All right, so in here, you notice a specific block that says multi-head attention, and that has 3 arrows going into it, right? And what does that mean? So if we look back to the self-attention mechanisms in both the encoder and the decoder, right? So for attention to happen, you have to have QKV, right? And we all know that. And in the encoder self-attention, you update encoded tokens by itself, right? So you have queries from encoder and keys and values from encoder. And for the decoder self-attention, you have QKV all from the decoder, right? So basically, in each component, you update the representation for each token with the representation of other tokens all in that same module. Right, but then what happens in the multi-head attention here is that if you think about it, if you have the English and the German sentence, right, and you have the full English sentence encoded by the encoder, and you want the decoder to generate the German sentence, and so when you're generating the next German token, then you actually want that token to attend to each English token. Right? And the reason for that is because you're not sure whether that token will refer to any specific English tokens in particular that's handled by the encoder. So then you want the query to come from the decoder, but you want the key and value to come from the encoder. Because you want, as with the analogy that I made earlier with our quiz, with our poll, you want the decoder token to ask each encoder token, what do you mean to me? Right? You want the German token to ask each English token what it means to the German token. So then that's the reason why for the cross attention, you have decoder inputs supplying the queries and encoder inputs supplying the keys and values. And that is all that is meant by multi-head attention or cross attention between encoder and decoder. It's exactly the same as usual attention as far as the formula is concerned. It's just the source of the QKV transformation matrices or the inputs is going to be different between cross attention and self attention. right? All right.
Josh?
Yeah.
Presentation slides are no longer shown on Zoom. Can you display?
It's no longer showing on Zoom. Does anyone have any questions, by the way? It's showing? All right, cool. All right. So then you have the updated representation for each decoder token from cross-attention, and then throw that into the feed-forward module, and that constitutes a decoder block, right? So this is essentially this highlighted block over here. And then what happens is you, since that block does not change input and output dimensionality, what you can do is stack as many of them on top of each other as you like, right? So you have this kind of setup. And each decoder output is going to have the same dimensionality. So then this explains everything in the transformer model except for this final component, which says softmax and linear, right? And the reason why you have linear is because you want to have actually the model output to be mapped to the token dimension, because otherwise there's no way for you to decode a token out of it, right? And so if you have 1,000 tokens possible in the tokenizer or in the vocabulary, then you actually want to map it to the dimensionality of 1,000. So then you can interpret it as the weight for each possible token at that place, right? So the linear does this job. And the linear weights are often, as I've written here, are often tied with the input embedding matrix. Just because weight tying is a useful technique, then you usually use the same weights for the initial tokenization or the embedding mapping and the final embedding mapping. So the only difference is the direction, right? In the original input embedding mapping, what you do is you map the token IDs to embedding vectors. And now you map the embedding vectors to token IDs. And then after the hidden representation passes the linear module, then you map that to softmax. So basically, what you're going to have there is essentially a matrix of TD times V. And TD just means time steps. So then if the time steps is 1,000, that basically just means your model is handling a sequence that has 1,000 time steps or 1,000 tokens. And V just tells you what each of these 1,000 tokens are, right? And as we did always, you pass it to a softmax on the TD dimension or on the V dimension. So then each of the TD elements is going to have a weighted. It's going to be a probabilistic weight for the token distribution. Same old story. All right. Now we have a poll. 30 seconds. All right, 10 seconds, guys. All right, so a couple of people are finished. So let's finish the quotes. Here, this should be clear to people, right? Transformer decoders can only be parallelized during training, and the reason for that is because you already have all the decoding tokens, so you can train the decoder to predict each token at the same time given all its preceding tokens. But your inference is actually cannot be parallelized because you cannot know what future tokens are before getting to all the preceding tokens of them, right? And then the answer D is pretty obvious. Again, any question, post on Piazza, we'll be happy to help. All right. So then this essentially finishes the discussion on the entire transformer architecture with the only exception. So this one, we actually added this for this year's lecture, I think. And the reason for that is that as models get larger and larger, you have basically a lot of these discussion floating around on the internet, on Reddit, all these papers. And then what you're going to find is people are talking about decoder-only models or encoder-decoder models or even encoder-only models. And then you're going to ask yourself, wait, isn't transformer a decoder-encoder or encoder-decoder architecture? Isn't this the transformer where this diagram involves both the encoder and decoder? So then if that's a transformer, how is it possible that you can have a decoder-only model, so to speak? How can a model only have a decoder, right? And I have had that problem or question when I was getting into the field, and so I thought it'll be helpful to provide an introduction to what that actually means here. So here is the canonical transformer, right? And as we talked about, the encoder is responsible for representation, and the decoder is also for generation, right? And that are the roles that they're designed for. So basically, encoder is responsible for outputting hidden states, given tokens, right? The encoder outputs hidden states, and the hidden states are interpreted as representation for these tokens, and you can use it in various ways. And the decoder is responsible for giving any preceding tokens generate the next token, right? And that's called generation, right? And you have the input and output of these different components. You have this masked language modeling constraint on the decoder only. The decoder can only see previous tokens, and whereas the encoder can see every token at once, right? The decoder has that property which is called autoregressivity, and the encoder does not have that, again, because of the causal mask, right? But then the big takeaway is that if you only have a decoder, then that decoder also has hidden states, right? Because we talked about it, the decoder block does not change the internal representation or the dimensionality of hidden states, right? So the decoder can also do the job of an encoder. There's no issue with that. It's just the decoder has that causal mask, which prevents it from seeing every token at once. But then for all the tokens that it has seen, then it does have the hidden states for that. So in that sense, it is an encoder. And if you have an encoder, on the other hand, then the encoder outputs some sort of hidden state at the end, right? And that hidden state, if it's a vector, it can be transformed to the vocabulary dimension. And if you do that, it can essentially interpret it as generating a token, right, as talked about. So the encoder can be used to generate, and the decoder can be used to generate hidden states. So then this is not a sort of big gap between these two dimensions or these two modules. And the takeaway is that you can have decoder-only models. And how it encodes is just by reading in all the different tokens one by one in the causal language modeling modality. So then it will have hidden states. And the encoder can be used to output information just by changing or by mapping the hidden state at the end to the desired dimensionality that you want. So then the takeaway is that decoder-only models and encoder-only models are possible. And it just so happens that the original transformer paper defined this as the transformer architecture. But then if you only have a decoder-only model, it's also not going to be any less powerful, because what essentially ultimately matters is the parameter count, right? If you only have a decoder-only model, but then that decoder has twice the count of an encoder-decoder model, so then that actually can be just as powerful as an encoder-decoder model, right? So this is what it means for you to have a decoder-only model. And in fact, you think this all makes a lot of sense, but then in the end, in 2024, what we see is that all the best models in language modeling, at least, are essentially just decoder-only models. What's that? So Mamba is different from transformer, and then we're talking about transformers. Yeah, but good literature. All right, so we have discussed everything in the transformer architecture. We hope that's clear, and please give us any questions you might have on Piazza. All right.
Okay, and now we move on to the next topic, which is basically how do we train the transformer architectures we just discussed. And previously, we've been discussing, we have these two separate parts. We have training and inference. And what changed with the transformer architecture is currently we separate the training in two separate blocks. We have pre-training and also fine-tuning. Let's now see how they're different and why it's useful to have them as a separate parts. So in pre-training, we have separate pieces. So we take a large data set, we build our model architecture, which is transformer-based, and we run the supervised training. It usually takes a lot of time, hours or days, and in the end, we receive this pre-trained transformer model, which is very general. It's not adapted to a particular task, but it's a good starting point. So it's been using lots of data, it learns some general things, and could be used as a parameter initialization for all future steps. But then we can move on to the fine-tuning. So we took this pre-trained transformer model, and then we provide a specific task-specific data set, which could be smaller, could be larger, and then we train our model to perform certain tasks. And then in the end, we receive a fine-tuned transformer model. Once we have this, then we can run an inference. And this pipeline is very useful because then we can separate, usually we can take a pre-trained model that's been trained by some other companies, and then we can fine-tune an our specific task. This will be very useful for you during your homework assignments, homework 4, as well as your projects, when you can use some pre-trained models that have been trained by some other companies, or some other organizations, and then you can fine-tune for your specific task, not to start from scratch.
All right. So I want to highlight something, which is that the reason why we have a different sort of training pipeline for pre-training and fine-tuning versus if you've taken a machine learning course in the past, you might not think about training this way. You might just think that we define a model and we just train it on the task, right? Why do we have 2 different phases for transformers specifically? And the reason is that transformers tend to get larger and larger. And with a large model, it's generally difficult to gather enough data just to train it from scratch, right? And the pre-training is just kind of invented as a sort of hack for you to do the actual training more efficiently. It's just meant for you to get a adequate, as Kate highlighted here, a parameter initialization for the actual training for your real task that you want your model to perform on, which is the actual fine-tuning, right? So as we see from here, training in transformers is really a big issue because you usually don't have that much data, and the computational overhead of training a transformer is usually much bigger than any of the other previous, classical machine learning models, right? And you guys have probably experienced that in your homeworks, part 1 and part 2, right? So what also happens is that people tend to invent what's so-called parameter efficient fine-tuning techniques, or otherwise called PEFT. And the way how it works is, if you look at my green little arrow over here, then you have a little green box next to the feed-forward that I've drawn here. So basically what it means is right besides the parameter or the weight matrix for the feed-forward module, you have a little bit of extra weight added next to it. And in the end, you just train that little green box. You don't train any other parameter in the whole model, you just train that green box. And you have to invent some way for that green box to merge into the inference of the model. So then that's actually going to be useful to change the model output into the way you want, right? And so this is just an illustration of what PEFT means in principle. In reality, that green box can go to any other model or any other layer, not just the feed forward, right? It can go to literally any of those boxes over there, and you just have a tiny bit of parameter that you train that's going to influence the whole model, right? And that's what's called parameter efficient fine-tuning, because you only train a little bit of parameters of all the parameters. You just train a fraction of them, and you do what's called fine-tuning there. And I want to give examples of 2 PEFT techniques over here. This is just going to be a very high-level discussion of what it means to do that. For the actual technical details, I would encourage you to look into the papers that have put the link right here. It should be an archive link, so it should be very accessible. All right, so the first thing is called LoRa. You've probably heard about it. It's called low rank adaptation. And what that actually means is, if you think about it, each matrix can be thought of as, can be decomposed into, lower rank matrices, right? And what lower rank means here, you can just think of it as meaning a lower parameter count, right? That's not what it actually means, but then you could think of it that way, right? So if you have a weight matrix that is, for example, A times B, you can decompose it to think about it, to think of it as the multiplication of 2 different matrices of dimension A times C and C times B, right? That will give you the whole matrix that is of size A times B. And the advantage of interpreting it as the multiplication of 2 different matrices is that the 2 smaller matrices, A times C and C times B, if C is small, then those 2 matrices is going to be much smaller than the original A times B matrix, right? If A and B is a million, like if you have a million times a million as a weight matrix dimensionality, then if C is just 10, then you have a million times 10 and 10 times a million, and those 2 will give you a million times a million. So then the 2 matrices that are described later is going to be much smaller than the original weight matrices, right? And so what LoRa means is just to decompose a specific weight matrix in that way into weight matrices that are way smaller than it. And then in inference, you just treat those 2 extra small matrices as extra weights in the model. And in inference, you just multiply those 2 matrices together, and you have a matrix that is exactly the same dimension as the original weight matrix. And you add that multiplication result to the original weight matrix. So then that will be enough to change the original weight matrix, right? So then it'll change the model behavior. But then you only need to train those two smaller matrices that get multiplied together. So that's why it's called parameter efficient, because those matrices are smaller, but then it also constitutes fine-tuning because model behavior does change. Right? So this is what LoRa means on a very high level. Again, this is a figure from the original paper. If you're interested, I encourage you to click into the link on the bottom here. The other example that I'm going to give here is called BitFit. And this one is even more interesting. So if you think about the QKV here, then those are essentially projections, right? And projection here can just mean a matrix multiplication, or it can actually mean an MLP, right? You can think of it as the input being multiplied to a specific weight matrix, added on to a bit weight or a bias term, right? And what BitFit does is it freezes everything in the model. It just trains the bias term. It just trains the B over here, is what BitFit means. And believe it or not, that's actually going to have a huge effect. So it's surprisingly very useful. You're going to think, wait, what? You just trained the bias, and that's going to change the model how it performs? So then the reason that works is that the bias is going to change the input to the next layer, which has nonlinearities, right? Which is being fed to the next attention layer, which has all sorts of attention and activation, MLP, and all that stuff. So then the bias actually has a lot of leverage in how the model performs. So then LoRa and BitFit are examples of clever strategies that people have invented just to train the transformer. And just with the breakup of the usual machine learning training pipeline into two different stages, these are all inventions. The pre-training and fine-tuning stages, the parameter-efficient fine-tuning techniques are all inventions that people came up with in response to the growing sizes of transformer layers. All right.
Okay. Okay, so we discussed we have different transformer architectures. We can have encoder-only models, decoder-only models, or just have a combination of both of them. Now let's discuss where can we use it, with what kind of data. And the answer is basically we can try to use it with different data modalities. We can apply it to language, to vision, to audio, and many, many other modalities like biological or physiological signals, everything. At the same time, it can also be multimodal. So we can try to use 2 or more data modalities and apply separate transformers to them. Let's discuss some of the cases. Josh will be presenting language case a little bit later in the lecture. And now let's talk about vision and audio and some cases of multimodal. So in computer vision, as you remember from all previous lectures, we had these high-performing CNNs, which usually provided state-of-art performance. And there are multiple attempts from different researchers trying to use transformers applied to the vision, applied to the images or videos. And usually they face multiple challenges with performance or scaling, and they've all been trying to find out a smart way how they can use transformer effectively and efficiently for image-related tasks. And the first idea that came and the key breakthrough was a vision transformer released in 2020. And now let's go into it, why it works and how it works. So as you remember with language, we have a single string of some text, and we broke them into separate tokens. So the first question that we have with a vision transformer is like, how do we break this one image into separate pieces? And the first idea was, what if we just have a grid, 6 by 6 pixels or some other combination, and then we will have a separate pieces of this image that we will feed back to our transformer. So what paper essentially says that we have this image, we break them into square pixels, and then we pass it, use basically the position encoding to encode where this piece belongs to in the original image, and then use transformer encoder, exactly the same that we explained in the previous architectures. And in the end, when we get the results, we run it through MLPs and use it as a classification. This particular setup was very useful, and they were able to achieve state-of-the-art performance with this. When we look about how it actually works, as you remember about CNNs, they were brain-inspired because they will work from the very lower features like the edges and dots to a high level when they combine different inputs into one specific image. When people try to visualize what vision transformer actually does, it's also very similar. So if we check on the second chart, basically the multi-head attention, they first of all, on the very, very lower levels of transformer, they pay attention to both global and more local features. But as we move on with the network, it will be paying close attention to global features, which is very similar to how like we will be seeing the performance in CNNs. And this innovation helped to receive and get the state-of-art performance for vision transformers, and they've been highly used. So this is for vision tasks. The next modality that we can discuss is audio. Audio is basically, was very similar implementation to computer vision. So we have this stream of audio as you worked with homework 1 part 2 and the homework 3 part 1 part 2. So you were working with a stream of audio spectrograms, and the initial idea was, what if we also split this audio into separate chunks and also feed it back to the transformer and get some classification. And so there are multiple models, and we pasted some links to particular papers. There are encoder decoder variants, there are encoder only variants that help us to get, using transformer architecture, go from audio to actually some classification. And some of the implementation, they still rely on CNNs, so they would incorporate CNNs and then transformer architectures. Next, so we discussed the vision transformer as well as the audio. We can also have a multimodal, because currently everyone is thinking about what if we just incorporate all this information we have, because people usually, when we think about ourselves, we're not just like perceiving just one sort of input. We usually have a corporate a magnitude of them we just see in the images and video and audio all together. And so we can also use transformer to account for that. So we can have a separate encoders for different modalities. For example, here we have a separate encoder block for image and then separate encoder block for text. We can then get all these representation embeddings, concatenate them, and then run for a specific task. So in this example, there is unit specific paper, and they basically were able to concatenate image and text, and they were able to perform 7 different tasks, ranging from object detection, vision, language reasoning, and many more. And the way how it works, so you can see that they have separate streams of encoders, they concatenate and then run for specific task. Second example we also wanted to introduce is Lava as well. It's been a very popular model recently. So here they work mainly, so they have an image, and they will be able to provide a prompt like what's on the image, and then the model would output, oh, the image contains such kind of objects. The way how it works, it has a separate vision encoder that takes in an image, gets the embeddings from the image. Also, it has some separate part as a language instruction that will help to prompt what's in the model, supplement it with a language model. So the way how it works, imagine we have an image, kind of like almost Mona Lisa, and we provide it to the model, and the model will read what's in the image, will read our input because we're saying, do you know who drew this painting? It will combine this both thing, both the image and our prompt, and will provide the description, how it all, like what's on the image. We've been heard that many students for the projects have been trying to use multimodal transformers, so this will be very useful, which you can use for your projects as well. Yeah. And now we move on to a special case about language.
All right, let me actually try clipping it on this time, see if it works. All right, hopefully it works. Is it clear? Yeah, okay, cool. All right, so the takeaway from that previous section is that the transformer, a large model, very versatile, with attention mechanism being invented for a specific type of relations between tokens in mind, can be applied to a lot of modalities, right? Including all the modalities we talked about. But then you look back to the original transformer paper, attention is all you need. The attention mechanism and the whole transformer model is invented with the specific task of machine translation in mind, right? So let's see how it does on language. So in mid-2017, this is going to be a higher level or the research angle sort of discussion on transformers. In that time, mid-17, you have the transformer architecture being invented with different modules intended for different tasks, right? The encoder is intended for representation, the decoder is intended for generation. So it turns out, as I said before, you can have a model that's only the encoder or only the decoder, right? And people have done that. So basically, right after you have the attention paper, then a little after that, a year, you have BERT, which is very famous, kind of the first LLM, so to speak, which is just the encoder, right? And GPT was just a decoder. And we're going to delve into how each of these works. All right, so the full name of BERT is actually called bidirectional encoder representations, hence encoder representations. So the challenge or the motivation for BERT people is that one of the biggest challenges, as I've written here, in the language modeling is the lack of data that is specific to your task, right? So basically that means both the input-output annotations and the token embeddings that can represent, that can tell you relations between each different tokens without even a specific task in mind, right? So then people have tried to do that without neural models in the first place. They have done word2vec, they have done Glove. These are sort of old technologies. If you're interested, you can search it up, Google it. But essentially what they do is they provide a pathway for you to translate tokens into embeddings, or basically into vectors. And the reason for that is because vectors allow you to do a lot of stuff. Vectors allow you to look up similarity. You can ask a vector embedding model. You can ask word2vec, for example, what is the relationship between king and queen as two tokens, king and queen, right? And you can calculate things like, the queen minus king is going to be nearly the same as woman minus man. So you have a lot of operations that you can do that actually tells you about semantic properties of these tokens with embeddings. And BERT is trying to take this to the next level in that it tries to train representation. Basically, that means train embeddings given a large corpus of task. So with the BERT model, you can have representations that can overcome the lack of task-specific training data, because then you have a sort of very general sort of embedding that you can apply to later tasks because they allow vector operations, as I described, right? And that is what representations give you. They give you a shortcut to do actual tasks. And BERT is just the encoder part of the encoder-decoder architecture, and it's pre-trained on this sort of corpus, which is considered very large back in the day. And then the pre-training tasks are these two tasks, which I'm going to go into in a minute. And then the training of BERT goes something like this. You have the large model of 340M, which is not really large by data standards. But then before LLMs, then that's pretty large. All right. So then here is an explanation of what MLM and NSP, the two pre-training tasks, really mean. But then before that, we need to look at this transformer diagram and think about what's the input and output for BERT, right? So the input is very obvious. It's just going to be a bunch of words. It's going to be a bunch of tokens, right? But what is the output? The output, it turns out, is just a bunch of embeddings, right? It's just a bunch of hidden states, which is going to be the dimensionality defined by the model, right? If the model dimensionality for the hidden state is 512, then that's going to be just of sequences, just a sequence of vectors of dimensionality 512, right? So, all right. So with that in mind, then what masked language modeling actually does is you take an input sentence, right? And you randomly mask a couple of tokens in the input sentence. So basically, here, I have an example right here. So you have this token basically replaced by the mask token. And you have the BERT model take in this specific, this masked sequence, and it goes through all the layers in the encoder. And then in the end, it's going to have an outdated or the updated representation of each token, right? And then you have what's called a prediction head that's connected to the last layer of BERT output. And then that's going to map the specific, only the embedding for the mask token to vocabulary size. So then you can interpret that as predicting the actual token underneath the mask. And what that allows BERT to be trained on is it's trained to have the most optimal representation for the mask token, which makes it the most likely for your prediction head to predict the right token, given the training strategy, right? And what that actually means is that BERT basically is trained to guess what the mask token is. And that, it turns out, is a fundamental ability in learning languages. For example, if you have a school kid learn a foreign language, then one of the common forms of exercise is actually just to mask out a word in a sentence and have the kid guess what the word is, to practice inflection and all the different grammars of that source language, right? And so here, you're trying to just teach BERT to do the same thing. And it turns out that with this training, BERT can actually invent optimal embedding, or not even optimal, but very useful embeddings for each token that is generally versatile and representable for downstream tasks. All right. So then what you also have is another pre-training task, which is called next sentence prediction. And what that actually means is you give BERT 2 sentences next to each other, right? And these sentences might or might not be next to each other in the original corpus. So maybe some of the times you just take 2 neighboring sentences and concatenate them together, connecting them by a separator token, STP separator token, and then feed to BERT. The other times, you get 2 sentences that have nothing to do with each other, and then you still do the same thing to concatenate them together and give it to BERT, right? And so in the start of in the sequence, you have what's called a classification token, which is marked by CLS over here, and you give it a BERT, it passes through all the encoding layers, and then in the end, you have what's called the prediction head that goes to the last layer of BERT, and that one just translates the representation of the embedding for the classification token to a binary flag, right? Basically, whether the first sentence is the parent or directly preceding the second sentence. And so with this training, BERT is able to guess whether 2 sentences have relations or have semantic properties that are related to each other. And the result is that BERT can not only guess words, it can also guess sentences, right? And so basically, BERT will be trained to understand sentences better outside of local representations of each word or each token, right? So these 2 tasks have made it possible for BERT to understand text in a very versatile way that is generally usable for a lot of tasks, right? So then I've kind of drawn an analogy over here. So you let BERT guess the properties of a token, you let it guess the properties of 2 sentences, and what's the next step, right? Yes, the next step is for you to get to guess the relation between 2 paragraphs or even 2 articles, right? And that happened not in BERT, but in later models. So the takeaway is that you can invent innovative pre-training tasks for the model to learn all sorts of things that turned out to be just fundamental abilities that lies in language material that we can get from Wikipedia and Google. All right. So then what it actually means when you have a pre-trained BERT model, pre-trained as in only with these 2 tasks. If you pre-train a BERT model with these 2 tasks, how do you use it for fine-tuning? You can use it on any other task by just getting a task-specific module, which basically means a prediction head, attached to the last layer of BERT output, right? And so if you have a classification task, for example, you can sort of formulate the task involving the CLS token, and then the last prediction head will just operate on the embedding of the CLS token. If you have a question answering task, you can train some extra vectors that map the BERT output to a specific answer range, right? So basically, the takeaway is that BERT can be pre-trained on these 2 tasks that have nothing to do with your actual task, but then they can the BERT can be adapted to your actual task by adding a task-specific module. All right. And so when you evaluate this kind of module or this kind of pre-trained model on the sort of go-to evaluation metrics of these 2, of question answering and summarization and all that different tasks, BERT actually is very performant, or even the best state-of-the-art back when it's just coming out. All right. So we learn these different things from the advent of BERT, right? We know that pre-training tasks can be innovative, right? Pre-training tasks can be sort of strange, even exotic, and even having nothing to do with your actual task, but then it turns out that the performance can grow when you pre-train the model on the sort of these strange tasks, right? And we also know that different NLP tasks, BERT shows that they are highly transferable with each other. So basically means that when your model grows performance on one NLP task, as long as within NLP in the same language, then chances are its performance on other NLP tasks are also likely to grow, given a large scale and large sort of a very versatile or a very diverse training corpus, then that's likely to happen. And scaling works. Again, this sort of parameter count is considered large back when BERT came out. So BERT is kind of what's called even the first LLM, people might say, and it actually has proven all these 3 points, which has marked the core driving force for the entire LLM field. Because right now, people are still operating on these 3 principles when it comes to working with LLMs. They just work on more fancy models and more intricate training strategies. But then under the hood, it's just these things, right? So then that was the discussion on BERT, and now we can talk about GPT, which has gotten more famous and eye-catching than BERT in general, because ChatGPT and that stuff. So the full name for GPT is called generative pre-trained transformer. I mean, the name says transformer, but in the end, GPT is just a decoder. It has no encoder, but then as I explained, you can have a model that's just a decoder and it will function just as well, right? So then the motivation of GPT is kind of similar to that of BERT. So basically, if you have large amounts of data floating around that we don't know how to use, can we somehow adapt those language material to be used in the specific language domain or be adapted to different NLP tasks, right? How do we make use of data that's just sitting around? And so GPT is just a decoder pre-trained on a lot of these, on this corpus, which involves Wikipedia and a bunch of books. And the pre-trained task is actually pretty simple. It's just to predict the next token because that's an inherent task that you can train a decoder on, right? The decoder is just designed to give you the next token. So then it's actually pre-trained just to predict the next token given all the previous tokens in your training corpus. And the parameter count is kind of small, but then again, it's kind of large back then. All right, so once you have a model that is trained, I mean, namely GPT, that is trained to predict the next token, given all the previous tokens, how do you actually use it for any task, right? And it turns out using GPT is even more intuitive than using BERT, because if you want to use BERT, then you actually have to have what I called a task-specific module or prediction head, and you have to attach it to the end of BERT, and you have to train it on some task-specific data, right? With GPT, it's even simpler. You just say it to the model. You know, we're kind of got used to it now, but back in the days, it's pretty surprising that you can just describe to the model what you want, and then the model give it to you, right? So let's say you want the model to perform summarization instead of manipulating the tokens or the embeddings and all the representations in any way. You just describe to the model, hey, summarize this article, please, and give it an article, and then the model will give you the answer. Similarly, for question answering, you can embed your question in some sort of prompt over here, and as long as the model recognizes that prompt structure from its pre-training or from its fine-tuning data, then the model will actually give you the right answer. So using GPT is actually more intuitive than using BERT, and that has to do with the pre-training tasks of these two models, right? GPT is just predicted, it's just pre-trained to predict the next token, so then you can actually have it perform just by having it predict the next token, which just means generating a sentence, right? And BERT is pre-trained on guessing the missing components in a sort of language material. So then you have to be clever in having the BERT do your job. All right. So GPT, the short takeaway is that it functions just as well, right? And then we have the same sort of 3 lessons from GPT. Self-supervision works in language modeling, and what that means is that the model is fed with supervised training material, meaning that the model is taught what is right versus what is wrong, but then the right or wrong or the training or the labels on the training material is generated by the model or is there already and doesn't need a specific annotation. And we also know that outside of the fact that self-supervising learning has such a surprising impact on model performance, we also know that language model can function as sort of a knowledge base. You know, before we have always, or machine learning researchers have always thought that each model is just going to have knowledge pertaining to the specific task that it's functioning on, right? But it turns out by training on Wikipedia, which contains a lot of different bodies of knowledge, you can have a model that is actually versatile in doing basically anything, and that's what we call a knowledge base. So again, this is kind of similar to the BERT point of different NLP tasks seem to be transferable with each other because they are, and the versatile nature of the attention mechanism and the big size of our pre-training corpus has to do with the fact that language model has emerged as knowledge base, and scaling works again. All right, we have a poll over here. I'll give you 20 seconds. Should be an easy choice. All right, let's close the poll, and here's the answer. All right, it was on an earlier slide. All right, so then kind of the last point that I want to make today with the transformer model and the different modalities and the specific application of language is the paradigm shift that it has brought about in machine learning. And what do I mean by paradigm shift? Right. So first of all, you have all these models that comes from the transformer architecture, right? You have encoder-only models on the left, you have decoder-only models on the right, you have ENCDIC models in the middle, you have all these models, and this has transformers has definitely taken over a lot of fields, including definitely language, and it has proven itself to be the most performant model that's ever been invented, right? And so with that growth in model popularity and specifically model size, machine learning researchers seem to be caring about a different class of problems than before, right? And what do I mean by that? Before the LLMs came about, what did machine learning researchers care, right? They cared about the data sets, right? How do we have task-specific data sets that contain the right answer for each task that you want to train your model on, right? How do you select a model architecture, or how do you, before LLMs, there are a bunch of model architectures, right? There's decision tree, there's like SVM, there are a lot of stuff, right? And how do you do transfer learning? So basically, labeled data for every task is scarce, meaning that there are not a lot of data to start with to train your model with. So how do you transfer knowledge from other domains? How do you sort of hack your model for it to learn more efficiently, even without data that pertains to your specific task, right? And then people always talk about, machine learning. The big question is, how do you avoid overfitting, and how do you make generalization better with your model, right? And so some of that still applies to LLMs. Is there a question? All right, never mind. So some of that still applies to transformers research after LLMs, but then since LLMs came about with transformers, then machine learning researchers are caring about these type of questions more frequently, right? So basically, how do you pre-train your model on something that is not your task, but then fine-tune it, so then you can actually have a model do the task, and in that process, leveraging large scales of data flowing around that are previously just not used, right? So the pre-training and fine-tuning. How do you make models perform on tasks that are not even trained on a single step, right? So basically that means transferring knowledge from out of domain to your task by some sort of prompting or even transferring of knowledge, right? So as I said, prompting. So how do you make models intuitively to the user? How do you make your model understand the task that you wanted to perform just by describing it in natural language? It was not thinkable. It was definitely not a thing before GPT or LLMs came about, right? The thought that you could just summarize an article just by telling a model to summarize the article. I mean, now we got used to it. You do it with ChatGPT every day. But then before LLMs or before transformers, generally you have to have a summarization-specific model for that, and you have to translate your token into embeddings for the model to work, right? But now you can just prompt your model and it'll do everything for you. And specifically, the most important type of question that has come about only after the transformers is, how do you even understand your own model? It was not thinkable that you will have a model that you cannot understand in classical machine learning. You have a decision tree, you know every detail of it, you know how it's written, you know how it's trained, you know what each weight means, right? In the transform era, it changed a certain way. What does it even mean, right? In what direction does it even change the model? People seem to be confused by their own inventions. Namely, they can't understand their model anymore. So this is what I mean by paradigm shift. So basically, machine learning has changed from a theoretical science to an experimental science, partly, concurrently at least with the invention of transformers. So what that basically means is, before people tend to have a model fully planned out on paper, they write a paper, they calculate every detail, they calculate the entire model, and then they only put it to work. And then they do experiments with the model written out that way to see whether the experiment results will be agreeable with their predictions, right? And now what happens in the transformer era is kind of the reverse, right? People have no idea what will happen when their model is running. And then they only form predictions, they only form theories after the experiments are run, right? They only observe their model and they try to explain their observations. Versus before, people usually had theories before their experiments. People usually predicted, or people already know what their model is going to do pretty well before any experiments. And right now it's kind of the reverse, right? And part of that is the growing size of models, and part of that is sort of the versatility of attention, and part of that is the ever-growing size of training data as well, right? So basically, you have sort of this paradigm shift in machine learning that's brought about by transformers. So then, if we go back, we will the reason why the attention mechanism came about is because we have this problem in recurrent networks, in that information is lost during encoding of long sequences, and that the sequential nature of the processing of these models basically disable parallel training, and that makes model not very trainable, right? And for that specific weakness, or these two weaknesses of recurrent networks, we have invented attention. And it solved these two problems in these three ways, right? It handles long-range dependencies, it enables parallel training, and it allows the allocation of dynamic attention weights based on inputs, right? So then, this is the end, right? Is there any problem in transformer-based LLMs? Of course there is, right? So just to give some food for thought, maybe you can say that, transformer, all it does, there are a couple of papers about it. What it does is just memorization and pattern matching, and it hallucinates all the time, and it does all these crazy things that you don't want in an actual model, seriously, right? So then, what's the solution there? So you can, of course, whatever the next architectural innovation is going to be, it's going to be just as important as attention, as long as it can solve these fundamental problems in language models themselves, right? So the takeaway in these two slides is just that each technological or architectural innovation comes for a reason, and that usually starts with the weakness of the last iteration of models, right? And with the current models or LCMs, then those were the weaknesses. And with current transformers, you can think about what sort of things that you want your transformer model to be better on, and whether that relates to an inherent weakness in the architecture. Right? And then that could be a cool research project if you're interested in it. All right, so with that, I'd like to make a final remark in the whole transformer architecture. So people might say, you might think that predicting the next token or even attending to each other in between different tokens is such a simple operation. You just multiply different matrices and get them back together and update what's so-called embeddings. And what does that even mean, right? How is that even important? It's true that language models are just trained to predict the next token, and there's nothing special about it. But to paraphrase Sam Altman, leader of OpenAI, in fact, animals, including us, are just trained in our genes to survive and reproduce. And yet here we are today. All right, so that's all we got today. Hope you guys enjoyed it. Please come down, ask any questions.